Okay, so let's see if you are live or not. Okay, cool. We are live. Okay, give me a second. Okay. Okay, so this is the first time. This is the first time I'm trying Streamlab desktop software. I used to use OBS. Last couple of time I used OBS only, which is good, but there are certain things which are like more convenient in the UI, and I think this one is a little bit better than that. So that's why we are going to use Streamlabs moving on. Hopefully it will work. Okay, so give me a second. Let me start the fan. Okay, okay, let's go. Okay, so what we are going to do here is we have already done the intro part of this developer training, and we have already done the state part of it, of the training, right? So what we are going to do in this particular live stream is we are going to look at the module time and look at the module sequence. So this stream is going to be a little bit longer as compared to the last two streams. So yeah, let's go ahead with the content. I will not be revising the old content. I'll be going through the training and see if anything comes up which I don't know. Then I might look at the PDFs for this developer training, and yeah, we'll go over that only very briefly if it is required. So. For the rest of the time, I'll go ahead and for small things, I will not look back. I'll take some assumption and move ahead. Yeah. Okay. So let's start with the time, and let's look at what this module includes. So I've already read this module time and SQL like a week ago. So I remember some part of it, but mostly I'll be going straight into it. Might not discuss something in details, might go and explain something in more detail as compared to others. So it all depends on what is more important and what is less important to know about the particular topic. Okay, so let's start with event and watermarks. So okay, so why does Flink support different notions of time? What are the different notions of time that Flink supports? And you code according to a particular notion that you choose. Okay. So there are different notions of time. First time is event time, which is the time when an event actually occurs, which is from the source side of it, first source side of it. So in this case, it could be a distinct communication a device or some server. So event time is the time when an event actually occurred, even after often carry event timestamps that were recorded by the edge devices detecting or producing the event. So these are the edge devices which are producing the event. So this is called an event time for this one. For when that event actually reaches the messaging queue, which is used as temporary storage between the event producer, and the backend system, this is for that purpose we have this messaging queue. Generally, it is some sort of queue like Kafka or something like some uh, I forgot what that some certain queue framework, right? Messaging queue framework. So let's look at what it says. The storage time is a time when an event is ingested by a storage layer, which is this layer or message broker. So it has message queue generally has message broker, which actually consumes the event or message and puts that into the queue. So that's what it's talking about, the message broker. This might be the first time that the event is being produced by a well-managed piece of infrastructure with reliable timestamp. So, okay, so Okay, so let me finish the explain why that is reliable. What does it mean by reliable timestamps? So storage time isn't a concept in the Flink API because we haven't reached the Flink APIs yet. It's a term we have made up so that we can talk about event timestamp that might be provided by the storage layer. That is, Kafka broker can add timestamp to the data they are ingesting, and we will look at that later, that how we are going to use it, if we are going to use it, and what are the trade-offs when we use this particular storage time or the time which is included by the Kafka broker. Moving on, we'll just assume that messaging queue that we are using is just Kafka. It's easier that way, and there are certain design decisions which Kafka has implemented, which is which is mostly generic for different messaging queues. So it's better to denote that as Kafka messaging queue. Okay, so using this mechanism is a a good idea in cases where the edge devices cannot be trusted to provide the meaningful timestamp. That's what I'm going to talk about. What does the timestamp means in terms of services, in terms of events which are occurring at what time. We'll talk about it. From Flink's point of view, it doesn't distinguish between event time and storage time timestamp. These are simply the timestamp already in the event by the time they are read into the Flink. So when that particular message actually reaches, or event actually reaches the Flink, sorry, Flink Flink cluster or API, that particular message already contains event time as well as storage time, which was included by the Kafka broker. So if the Flink API implementation want to use those timestamps, it's available to use. Okay, so this is the basic standard thing that it is trying to say, that this is another type of notion of the time that Flink actually has or can be used in Flink APIs. Okay. Okay, let's talk about the timestamp notion, right? So what does timestamp means in terms of service, in terms of what does timestamp mean actually when we are talking about an event and it occurs at certain timestamps. So what you need to know about basically about the timestamp is timestamp on a server is is not always correct for obvious reasons. So there are delays, there are the timestamp that machine VM has is maybe delayed or is not synchronized with the actual server. It's not possible to have all the machines in the world to have the same timestamp because they need to coordinate via network, which also takes some time. So it's not always possible to determine the timestamp, a single unit of timestamp for all the services that we have. So what we do is we use a relative notion of time. Okay, so when it says that this is an event time, so what it means by that is the time which is observed on the edge of the event which has been occurred. So this is the one notion of time. This is the one format of timestamp which was noted when the event was created. And when that particular event reaches the messaging queue, it might take messaging queue, it will record the time for that particular event. So for example, let's say there are two events which are occurring. One is occurring at timestamp 1, another is occurring at timestamp 2. That is event time. Okay. And when those events are sent to the messaging queue, the timestamp 2 event reached the messaging queue first, and timestamp 1 event reached the messaging queue second. Then what happens is messaging queue will note the timestamp of event 2 as less than the timestamp of event 1, even though those events were produced in the reverse order from the event producer. So for messaging queue, it will see the order of those events differently as compared to event producers, which is event time. So event time is 1, 2, and the messaging queue received receive those events at certain time, those times are called messaging queue storage time in this case. So these are relative notions. 1, 2 is from the perspective of event time, 3, 4 in perspective of storage time. And even in the storage time, there might be different. There might be so then so messaging queue might have different machine internal to cluster, so they might have different timestamp, which which may not be synchronized with each other. So that's also relative. So that's one of the things about the distributed systems is having a notion of time is very difficult to maintain across the communication, across the different VMs, across the different infrastructure when we are communicating. So it's one of the most difficult part of the distributed system. Okay, so moving on from that, let's go to the next. I hope that is clear. We can talk about it more when we go through these slides, but I think that's a basic way of understanding the time in terms of distributed systems. Okay, now let's talk about. So there is another version of time, notion of time in this case, which is called ingestion time. So this is happening at the Flink data source. So you can configure your Flink application to timestamp events as they are ingested to the rest of your application. These will appear to be event timestamps, but they will not be reproducible. Okay, so what happens is when those events are consumed from this messaging queue by the Flink data source APIs, it will timestamp each of those events according to the timestamp of the particular VMs that is consuming them on the Flink data source side. And that particular time is called ingestion time. And that is what for the rest of the Flink application will denote as event timestamps. So rest of the application on the Flink side will consume that particular timestamp which was generated at the Flink data source as event time. And the reason it says that they are not reproducible is because the event okay, so let me okay so so they're not reproducible because it's a possibility that those event might be consumed by the Flink data source API in some other order, okay, and at different times. So let's say if we try to so for example, if a message is consumed on the Flink data source type and that message is lost, and we try to get that message again from the messaging queue, then we will get a different timestamp, or we will mark that event with a different timestamp because it's occurring in future. So the timestamp will be different than the old timestamp that we assigned to the same event. So that's why it's saying that they are not reproducible. We don't know what was the time when the event first actually reached the Flink data source. Okay. Okay. So as we discussed in the last couple of modules, after the events are consumed on the Flink side, those events are passed through different operators. We parallelize different operators to maximize the output and create a stream out of it. And we will put those stream objects into the sink that we have. That sync could either be another streaming platform, a stream framework, or the sync could also be a database or something like that. It depends on what we are using as stream. Another thing which I should mention is, in this case, whatever time that each operator node sees is called processing time. So whenever the event is particularly reached on the operator side on a particular VM on a particular node of the operator, it has certain time on the VM, and that time is considered as processing time. So when we say that we are going to process this particular window inside this particular processing time, we are using that time on that operator side to operator node side to create those windows. Okay, so the processing time is different. Ingestion time, which is nicknamed for the rest of the Flink framework as event time, is also produced by the Flink data store, which is not reproducible. There is this messaging queue time, which is called storage time here, and there is this event producer time, which is called event time here, which is different from the Flink data, which is different from the ingestion time, which is mentioned. Okay. So let's go to the next thing. And the processing time for an event is the system clock time, while the event time of an event is deterministic. The processing time of an event is a system clock time. Okay, that's what I mentioned, right? Each node has a system time, which each node operator node has a system time, which will be called as processing time. So while the event time of an event is deterministic and immutable, the processing time is always changing. So, okay, so what does it mean by that? So, when an event occurs, it passes through this particular source. Okay, then let's say the first time the event was sent to this particular operator, and this particular operator consumed that event, created a temporary state, but something happened, the abort happened on this node, or node goes down. Then how do we make sure that we don't stop there and we have this fault tolerant for the failures of those nodes? What we do is we restart those um, re- redo those operations again, and at that time when we are redoing those operations, the processing time will be different because we are doing that in future, similar to what I mentioned about event time here, which are not non-reproducible. Okay, but yeah, the processing time is always changing. If you run any event time based pipeline more than once on the same data, you will get the same result because event time is not changing. When you have already consumed the events from the messaging queue, that event time or ingestion time will not change. Moving on, we will just call the ingestion time as event time. Okay, so that event time will not change. Okay, but if you are running a processing time based pipeline more than once on the same data, you probably will not get the same result. The reason for that is, as I mentioned, the processing time will be different for each event if we try to process those events again in the Flink operator after a failure. So you will get a different time. It might happen that a particular event previously was occurring in a window 1, but after reprocessing it, that particular event is happening now in window 2. So the event might, the output, the result that you are going to get after executing those operator might not be same, probably will not be same. This determinism and the ability to reprocess historic event is a major advantage of working with event timestamp. That is very understandable. If you have consumed the events on the data source side of the Flink, and if you run the pipeline based on that event time, then you can do the same operation even after failure. The operation will result into will give us the same result as it was giving before the failure happened. So it kind of, when you are using an event time from Flink's perspective, it will give more deterministic output as compared to when you are doing the processing based on processing time on the operators. So that's one of the things which event time and processing time has the difference of. Okay, give me a second. Let me come back. I need to go to washroom. Okay, now let's go over the next slide. Okay, so events are often processed out of order. Event may take different paths, experience different delays, which is understandable, right? So the same example that I gave for t equals to 1 and t equals to 2. So let's assume that t equals to 1 is the event time and t equals to 2 is the event time for another event. And those two events reached the operator at different time in different order as well. So the event time will be processed in that case out of order as compared to event time. Okay, not as compared to processing time. The processing time is executing in the same order as the processing time progresses. So that is out of order by the event time, or even different paths or different delays. That's what yeah. Here the first event occurring at time 2 is delayed quite a bit longer. Give me a second. Okay, give me a second. I'm just trying to message someone. Okay, so yeah, let's go to the next one then. Here's the first event occurring at time 2 is delayed quite a bit longer than the second event that occurs later at time 2. The result is that they are processed out of. This is one of the things with the communication, right? So you might be talking first, another person might be talking afterwards, but it might happen that the other person's communication reaches the destination first and your communication reaches the destination after that. So those events are called out of order event in this particular slide. Okay, so let's look at the out of order stream. So these advantages of working with event time do come at a cost in terms of adding quite a bit of complexity. When you operate entirely in processing time, then nothing can ever be out of order with respect to time. That's obvious because we are executing things based on the we are executing on. So there is a timeline which is going on the operator side, which is the processing time. Okay, and if you are executing according to the processing time, we are consuming the events which are there in this particular operator in that particular order. So we are executing in processing time is always in order. Okay, those events are always in order. But if you are executing based on the event timestamp, then it becomes an out of order question when you are executing on the operator side. But once you begin to perform distributed operations on events that have been timestamped upstream, then you must be prepared to deal with out of order events. So timestamped upstream here means you are timestamping the events on the data source side in this case, which will create event time. And if you're processing based on event time, uh, you will you'll have to deal with out of order events. Here we see a stream arriving from left that only very roughly in order. The events timestamp measured in second are shown in the box. That is fine. Okay, so here we see a stream arriving from left That is only very roughly in order. Okay, that's fine. We have already done it. Sorry, I'm a little bit distracted. Um, so the goal here, the operator here that we are trying to do is we have certain events, and we want to count the number of events which are occurring in each 10-second time window. Okay, so as it is arrived into the appropriate window, which is created lazily whenever the first event is assigned to it. Okay, so this is the order that we have. Let's see how we process this and we count events in 10 seconds time window because it's out of order, right? It's not a straightforward assumption that all the 1, 2, 3, 4, 5 in all the 10-second events will be at the starting of this particular queue. So we need to make sure that we are counting correctly. So let's first go to the first window, which is from 00 to 10. Second also third goes to the second window that we have created, which is for 10 to 20. And we do this, and we keep on distributing this, all of these, right? So eventually our window count emulation will have to stop waiting and producing for the first window. Okay, so like after a while, it seems like we might not get any more event for the first window. It is possible, right? How long we can wait for this particular window to have the event? Okay, so you have a god like view of the streaming content and look ahead and see a six coming, but the stream processor has to take event as they come and make decision based only on what has already been processed. Eventually, our window counting applications will have to stop waiting and produce some result for this first window. Exactly, right? So we can wait longer and be more confident that the window is complete, or be more impatient and produce ready result quickly with a greater likelihood that they are incomplete. Okay, so let's complete this. As a practitioner, managing this trade-off between completeness and latency is something you want to be able to control. Watermarks, which are used to look at the mechanism Flink provides for this purpose. Okay, so what is happening here is we have this particular window from 0 to 10, and we can keep on putting events in this, right? But how do we know that this particular window is completed? How do we know that, let's say we processed all of these events, we processed everything which was in this particular window. How do we know that there are not going to be more events which might come in future which lies in this particular window? We cannot know that. So either we can wait for all of those events to come indefinitely and produce the result at the end um, if you can do that, but or or what you can do is you can say like something like, you know what, I'll wait for 20 seconds for this particular window to finish, and I will finish in this window when 20 seconds happen. At 20 second I'll finish this, at 30 second I'll finish this particular window. So I'll wait for 10 more seconds for each window to finish, and for the rest of the events which comes after that window, we'll do some late processing on that later. But that's a trade-off that you have to make. Either you want to have completeness of this particular operation, or you want to produce result fast. Okay, so that's the thing. Okay, so watermarks marks the passage of event time. So that's what the watermarks are used for in the Flink. So Flink provides a mechanism to tell these streams, to tell this operator that, you know what, this time has passed. Okay, so we'll go into look into the how does watermark handle this particular situation, but Watermark is provided to handle that particular trade-off. You can change that watermark and its configuration to look at to change this trade-off between completeness and latency. Okay, so here the figure shows some watermark that has been inserted into the stream. Each item flowing through Flink is a stream element. Okay, watermark is a kind of stream element whose payload is simply a long timestamp. Okay, each of your application event is wrapped in a stream record, which is another kind of stream element. So all of the elements which are there in this particular stream are called stream elements, and there is a subdivision which we have been created for watermark. It is stream element. It's called stream element. No, sorry. It's for watermarks. It's called watermark event. Watermark event. These are watermark events. Okay. Another type of event is simply the record event, which is being produced by your application. So all of these 21, 14, 10 are stream records, and all of these W here are watermark events. See, if you look at this, it will have certain timestamp. Okay. So each watermark will have certain timestamp, and the other events will have the event time which has been assigned to this particular event, and the payload, mean payload, which was sent by the source. Okay, so let's look at the watermark T indicates the stream is now complete through a time T. So what? Okay, so let me tell you what does the watermark here represents. Here watermark represents that we have reached the time 5 for the okay, so how do I frame it? Okay, so what does watermark 5 here represents is it tells this particular stream that, you know what, we have reached the end of event time 5. So, and similarly for this event time 9, here we have reached the event time 9, here we have reached the event time 15, 17 here. So what it helps is there are certain events which we can trigger after a certain amount of time, as we mentioned in the last slides, right? We will just wait for each window to complete for 10 seconds. In that case, what happens is as soon as we see a watermark of W20, we will process this event, send and do the operation on this stream particular window, and produce the output of it. We will not wait any further for that for this particular window. So that's what watermarks helps with. It kind of creates a separation among the events that a particular event time has been complete or passed. Okay, so watermarking is not automatic. If you choose to use event time processing in your Flink job, then you must arrange for watermark to be provided. In most cases, the simplest solution is to extend so Flink's bounded out of order watermark strategy, which consumes that event are arriving with some bounded amount of delay. In this example, we expect our event to be no more than 6 seconds out of order. So we have configured our watermarking accordingly. So when we see an event with a timestamp of 21, for example, we can be fairly confident that all events with a timestamp up through 15 will have arrived. Okay, so in case of our earlier example, it was 10 seconds. In this case, it is 6 seconds. So when the 21 timestamp arrives, it says, you know what, the event time of 15, all the events which occurred at time less than 15 or equals to 15 has already occurred. So we can process that particular window, whichever window is depending on that particular event time of 15. Of course, right behind this watermark 15, we have a stream record that is late. Its timestamp simp is behind, 6 is behind the watermark. We'll look at how to handle late event shortly, but first, let's understand how Flink uses watermark. So, we want to understand, so I already explained how it's going to use it, but this is just for bounded out of order. This particular strategy, it has watermark strategy, it has um, to put these watermarks depending on the event times it's seeing in the queue. And we can use this strategy to finish the operation for each particular window and assume the completeness of that particular time window. Okay, so this watermark strategy observes the timestamps in the events, keeps track of the largest timestamp seen so far, generates watermark by subtracting the bounded delay from the max. So what happens here is there is a for event which so it maintains a maximum event time it has seen. So at this point maximum time is 4. At this point maximum time is still 4. At this point of time maximum time is 11. Now what happens is in this particular strategy we define a particular threshold, the particular diff between the event time which has occurred and the watermark that we need to create. So for this example it has 6-second delay. So what it says is whenever there is a maximum, so what it does is it puts a watermark into the stream of timestamp, maximum timestamp that we seen till now minus that particular delay, which is in this case 6 seconds. So 11 minus 6 is going to be 5. So it puts a watermark of 5. Something similar happens here. When the maximum is 15, 15 minus 6, it puts 9. Something similar happens here, 21 minus 6 is 15. Something similar happens here, 23 minus 6 is 17. And it kind of gives the indication that, you know what, this particular event time has finished. This event time of 5, 9, or 15 or 17 has passed at this particular time. So all the windows that were depending on that particular event time can be processed. Okay, so generating, so this I already explained. So this is the processing time. Processing time is continuous, right? So it's just on a VM, it's every event is getting processed. So processing time is always going forward. But event time is out of order, right? So that's what it's trying to say. Processing time is continuous, event time is adjusted based on what we have seen, what kind of events and what kind of event time that we have seen in the queue, in the stream, sorry. Okay. Flink has two kind of internal clocks, one marking the flow of event time, another connected to processing time. Processing time clock moves forward automatically on their own, obviously, but event time clocks are connected to watermarks in your data stream and are only advanced when the watermarks arrives. So what it's trying to say is until the watermark arrives, we don't know that the particular event time has passed. Stream doesn't know that. Okay, so we need to provide a particular strategy which puts these watermarks in the stream to let us know that this particular event time has passed, and we can process the all the windows which are depending on that. So you as a Flink developer, application developer, so you as the Flink application developer are responsible for moving event time forward by arranging the watermarks in the string. Okay, so watermarks are obvious, right? So If you are doing event processing of the events based on event time, you need to provide watermarks. Otherwise, those windows that you are creating will never be finished, will never output, because it doesn't know when a particular event time has finished if we are not putting the watermarks in the stream. So two kind of timers, processing time timers triggered by the system call me at 8 p.m. Another type of timer triggered by watermark, call me when you know everything from before 8 a.m. is finished. Okay. So the concept of timer here, right? So concept of timer in Flink is very much similar to what we have in any other programming language. You can think of it like an alarm, and each timer has certain indication what it's trying to say. So, for example, if you have processing time timer, it's telling you that this particular processing time has passed. And if the timer is event based, it's going to tell you that this particular event time in the stream has passed. So it triggers when timers will trigger when a particular event time or processing time has passed. And the way we tell that event time has passed is by putting those watermarks. So event timers will look for those watermarks to trigger these timers. So just as Flink has promotional, two kinds of timers are available in key process function. So these are the timers which are present for each key process function, which we saw was the rich function in last two videos, part one and part two. Um, okay, so two kind of window processing time. Window include whenever event happens to process during the window. Use processing time timer processing time windows are triggered by system clock. Obvious. So including only those events whose timestamp belongs to the window. Okay. So use event time as event time windows are triggered by watermarks. As I said in previous slide, event time timers are actually triggered by watermarks. So whenever we see a watermarks of a particular timestamp, we trigger all the timers, all the event time timers which are less than equals to that particular event time which is present in that particular watermark. So generating an appropriate watermark that accommodates delayed and out of order event typically requires processing event from the next window before closing the previous one. Obvious. So the way we do it with including the watermarks is like this. So we have the event timers for different windows. We created different windows, and when we saw W15, all the timers which are less than equals to 15 will be triggered. So this timer which was set for 10 will be triggered, but not this because this is greater than 15 and this is greater than 15. So this will be triggered as soon as we see this particular watermark. So this will trigger and this will process the output. So this was triggered, we have counted everything and it was outputted into the sink. Similarly for rest of the watermarks. Okay, so let's go to the next slide. So let me put it into the stuff. Okay. 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 So the concept of lateness in terms of Flink, right? In terms of event processing, I guess. So what happens if, let's say, if you remember, right, W15, when the W15 happened, we said that you can process the window of 0 to 10. But if you look at this event also lies in that particular window. So this event um, is called late event. Okay, so whenever the timestamp of the event is less than equals to current watermark, it says it's called a late event. So it says it is equal to. Okay, got it. So when working with event time, not only will event arrive out of order, there can also be leap. In our example, we have an event from time 6 that arrives out of the watermark for 15, so it's definitely a late event. Okay, application defines different policies to handling the late events. So you can implement certain APIs to deal with the late events, and there are different ways to implement this. Depending on the business application, it could be different for different implementation. So, but it is available as an option for application to process the late event. If they want to ignore it, they can ignore it. If they don't want to ignore it, they can do process. They can actually process these late events. In general, it's not possible to accommodate arbitrary late events because this would require keeping around an ever-increasing amount of state. Instead, the best practice is to accommodate some bounded amount of lateness and eventually expire and free whatever state was being kept. So, so remember that time window that we use from 0 to 10, and we calculated the count as 4. So that count 4 is somewhere stored as in the state in one of the operators, right? And we can only store so much and for so much time. And if we don't free those state, it will keep on increasing. That's what it says about ever-growing state, right? So let's say that late event occurs after we freed that state, then we don't have the count to increase, right? We don't have the state to increase the count from 4 to 5. We don't have that particular state. So what we do is we can just ignore this particular event at that point of time. But in generally, most of the application just use that out of bound threshold to handle the late events. Okay, so by default, once a window fires, state is freed. Without a state, late event cannot be processed. Of course, as I mentioned, 4 is not there. We cannot increase it to 4 to 5 when the event 6 is coming. The window API supports allowed lateness. So even after this particular stream 010 000 to 10 was processed, when W15 came, we can still wait for that particular state to be released even after 5 seconds after that, right? So when the 6 comes, the state is still there, so we can just process that particular state and make that count from 4 to 5. So with sufficient allowed lateness, the 6 will be added to the first window and an updated result will be produced. Okay. Allow supports the notion of allowed latency, which defaults to 0. By default, it is 0. This allowed latency defines an interval after the window's initial firing, during which Window state is retained and the late event can trigger additional window firing. That's fine. Okay, so we are going to look at the life cycle of event. What happens, what sorry, give me a second. Okay, so we have this event which is created. That event waiting for events from time before t, current watermark reaches, and that particular timer is triggered. We process the events, and then after that we are waiting for the late events also. We have that threshold I mentioned in the last slide, which is 5. We'll wait for that particular threshold. We'll keep on maintaining the state. We'll process the late event as well, and after that we'll free the state, and those late events which occur after that window, after that time, will be just stopped because we don't have the state. Without state, we cannot process those events. So this slides illustrate a general pattern followed by the full streaming application. Because events arise out of order, it's common to not be ready to take action immediately when an event arrives. If instead it's necessary to wait until any event has arrived, this is done by setting an event time timer that will be triggered when the current watermark reaches the timestamp of the event in the question. In the meantime, some state after the event can be recorded. Okay, so okay, so this that will be triggered when the current event of the event in the question. Okay. In the meantime, some state about the event can be recorded and to be used when the timer fires and the action is performed. The late event will also need access to that recorded state information. Then the second timer is used to define another interval. So that lateness, right? We mentioned about 5 seconds. So that particular timer is triggered after the 5 seconds of the first timer which was triggered. So when that second timer triggers, we can clear the state and we can process the events which have come till now and keep on counting, and then we can clear the state. Otherwise, the state can be filled as soon as the section is performed. Okay, so that's what it means. So this is the first slide. Okay, So the Flink support different notions of time. We already uh, talked about it. With event time can be out of order. Can expect deterministic result depending on event time. I can process historic and live data with the same code, as you mentioned. Event time application responsible for providing watermarks. The watermarks are only needed when we are processing based on event time, and we can decide how to handle the late events. And the streaming application must trade off completeness for latency. So that's what I mentioned earlier, right? So there is a trade-off between completeness. Either we wait for infinite time and don't produce any output, or we can provide or we can produce output when the event comes. So there is a trade-off which needs to be managed based on the watermark strategy that we use. Generally, the watermark strategy is out-of-bound strategy that we can use, which is the by default. And can wait longer to have more complete information before acting, can wait less to reduce latency. What are the mechanism for managing this trade-off? That is fine. We already discussed about this. Okay, so let's go to the next slide. Okay, this one is longer, 28, but let's look at how we do it. Only relevant when doing event time processing. Of course, the guess about the progress of event time in the stream. It is inserted in the stream by Watermark Generator. Okay, so when you are using a particular strategy, right, it has two things in it. I think one of them is Watermark Generator. That generates the watermark, inserts into the stream. It carries, and that particular watermark has timestamp t, which is called current watermark at that point of time in stream. So indicates that stream is probably now complete up through the time t, less than time t. I previously mentioned it was less than equals to time t, but it is less than time t. So event time timers are triggered by watermarks. Of course, event time window rely on watermarks to know when the windows are complete. Of course, pattern matching on stream depends on being able to sort streams on stream, which also relies on watermarks. Okay, so pattern matching here. So what does pattern matching means? So there is a particular business application which looks at the events which are occurring in real time and trying to figure out certain pattern out of it. For example, let's say we are looking at a financial application, and that application has 10 events, and those are out of order. As we mentioned, if we are using the event time as a timestamp, then we have to first sort them in the state, and then we need to analyze those events, detect patterns in those particular 10-second or 20-second, whatever the time window that we are using, and try to figure out if certain pattern is matching or not. Okay, and that whole processing of that window only occurs when we have watermarks. So when watermarks triggers the event time timers, and those event time timers actually processes all the state and produce the output out of it. We look at the actual implementation in future slides. Okay, so how is event time measured? Timestamp and watermarks are longs, and they must be comparable and measure the same thing. By convention, they measure time as milliseconds, since the epoch, data stream, and Sql API for event assumes this. Okay, so it's generally measured in milliseconds. But at the lower level of leaking, event time is pure abstraction. Event time can be measured in nanoseconds rather than millisecond. Event time can be represented as monotonically increasing sequence number also. So we look at the event time as a millisecond, but it could internally be implemented in form of nanoseconds, or it could just be a version vector, or it could be just an counter that we are using internally. Okay. 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 So, what are the different types of stream elements that you mentioned which exist in the particular stream, right? There is stream record which comes from the application which contains the actual payload that we have to process. Another one is watermark, which we already discovered. It contains the timestamp. Another stream element is watermark status, which contains either it is an idle, watermarked is an idle state or is an active state, so that it doesn't have to wait any longer if the watermark doesn't arrive. And another thing is latency marker it can be compute. It can be used to calculate the telemetry for the complete architecture. We can calculate whenever these event occurs. We can calculate the latency that we are seeing of processing those events. Okay, so we look at sorry. So we look at how we process all of these events. So there is this event, then we have the stream record, which will contain the actual event payload and the timestamp. And this will be the timestamp, like event timestamp that we mark when we are marking each event on the source side. So we are kind of wrapping the actual payload inside the stream record. And watermark, we already know that it just contains a timestamp which tells you that this particular timestamp and event time has already passed, and it's in millisecond. Okay, so how are watermarks propagated? Okay, so if you remember from last slides, so watermarks are propagated in streams, right? And those streams are passing through each operator. So each operator and source, right? So for example, here it has all this particular node has already seen a watermark of 10. So it has assigned its local watermark as 10. And whenever this watermark changes, it passes that watermark event to whoever it is passing to whoever the destination is, right? So it will pass it to all the nodes which are connected directly to this particular node. So it will pass one W10 and W10 here. It's still passing here in this category, guys. In this case, it has already seen 17 and it has still not sent that particular watermark to this particular node. So what happens? And similarly, in this node, it has seen certain watermarks, okay, and it has seen watermarks coming from here, watermarks coming from here. So what this node will do is it will take the minimum of the watermark it has seen. So it only progresses at watermarks when the minimum of all the watermarks that it has seen from different sources of stream progresses. So it has only seen the 5 from minimum from both of these streams, so it has just 5. But when it gets W10, it will still not change. It will. Okay, so it has already sent. Okay, so this is the thing, right? So this is maintaining a state here. It is maintaining state that from source 1 it has only seen 5, and from source 2 it has already seen 17. So this 17 watermark has already been sent and processed already by this and updated in the state. Same thing here. But when it sees W10 from this, what it will do is it will update the source 1 to 10 here and here, and will take the minimum of them and it will come out as 10 for both of them. It will change the watermark here to 10 here, see, and it has still not changed to this watermark from 5 to 10 because it has not processed this particular watermark. So that's how we propagate watermark across the nodes. Okay. Okay, so as I mentioned, if you remember, in this stream only, so each strategy has two things. First is which actually generates the watermark, and another thing is the event trigger, time trigger, I guess. Okay, so first need is creating the watermarks. Second thing is producing the event timestamp for every event. Okay. Okay. So yeah, let's look at what does watermark strategy contain. I remember that it does contain something which generates the watermark, and I think it contains something which actually triggers the event timers when the particular watermark is reached. I think so. So watermark can be applied either after your source, in your source, preferred but not possible. That's a different thing. We'll look at that later, I guess. But it produces for each event time processing, Flink needs event timestamp for every event. Okay, got it. Okay. Okay. So it doesn't trigger the event timer. What it does is each strategy looks at each event, gets the event time out of it. Okay, you could use different event time, right? You could just use the time which was produced by the IoT device, or which was inserted by the Kafka queue. Okay, so all of these different notions of time that we saw could be used, and that is what it has. This particular time set that we are creating for each event could be different. Different application gives different notions of time, right? So it provides a lambda function. We can provide it a lambda function which actually extracts that event time, and there is another lambda function which actually creates these watermarks based on those event time that we have. taken, right? That's what it does. Okay. Okay, so another thing, right? So how do we, when do we, okay, so watermark strategies, so this strategy can be applied on the source side from where, so this source is not the same as, um, is not the same as the data source, Flink data source. This source is the Kafka one. So Kafka, the streaming queue, messaging queue can already include these watermark messages in those queue, and in those queue, or we can do it later at our data source. So that's one of the things. So after your sources, which is the Kafka source, or in your source, which is the Kafka source. So after the Kafka or in Kafka. So those are the two things we can do. There are different trade-offs for each type of insertion. We'll talk about those trade-offs later on this PDF. Okay, so let me come back. Let me come back. Give me a second. So let's look at uh, so what does the watermark strategy, the different strategy has provides, right? So there are two things. There's a timestamp assigner. So each so I mentioned, right, each event we can use a timestamp, event timestamp of IoT devices which generated those event, or the timestamp by the Kafka queue or something like that, right? You can use those timestamp as the event timestamp, which is what this timestamp assigner does. It assigns timestamp to each event which it is consuming. So sets the timestamp field in the stream record, collects the information produced needed to produce the watermark. That is the timestamp that we are assigning to each timestamp. So we take the maximum out of each event time, and this watermark generator actually generates the watermark based on those maximum timestamp that we have seen in the event time. So on demand periodically based on execution config, generates watermark on demand periodically based on the execution config get auto watermark interval as a part of processing each event. Okay, so it generates the watermark using this particular configuration after a certain time of event has been passed. So generally that is 20 milliseconds. So each 20 milliseconds this watermark generator will be called, and it will look at the maximum time it has seen, and it will generate the timestamp based on that. watermark based on that. Watermark strategy is for bounded out of orderness, duration of milliseconds. Okay. Mhm. Okay, so let's look at uh, by default strategy. So there is this strategy we mentioned about bounded out of orderness, right? So in this case, what we'll do is after each 10 milliseconds, um, we will create a watermark. For example, we have seen 21, okay, and then what we'll do is we'll create a watermark for 11. We saw maximum of, let's say, four. We'll not create watermark for it. Let's say we see a maximum of 11 in the timestamp, then we'll create a watermark for one. So typical case bounded out order for monotonic timestamp, special case ascending timestamp used when events are perfectly run, watermarks are not delayed, no late events. If you're lucky enough to have stream data strictly in order by timestamp, you can use result. This will produce a perfect watermarking. Do so with no delay, since there is no need to wait for out of order event. The watermarks will exactly match the timestamp. So let's say we have a stream which is already sorted 1, 2, 3, 4, 5. Then if we have the duration of, like, let's say if we have the strategy of 100 runs timestamp, then after one event of 1 is processed, it will put a watermark. After event 2 is processed, it will put a watermark. After 3 is processed, it will put a watermark. So it will it will kind of consider that each event is in itself continuous and monotonic in terms of timestamp it is seeing. So we'll keep on closing the windows whenever the timestamp watermark timestamp is increasing, and there will be no late events because we are increasing the timestamp monotonically. So watermark strategy, no watermarks, especially when using the new unified source interface in an app does not watermark. Okay, okay. So we are talking about all of these. We are talking about watermarking, right? For something, some processing which we were going to do based on the event time. But what if we are not processing based on event time, right? In those cases, we will use this particular strategy which doesn't put watermarks inside the queue, inside the stream, sorry, not the queue, inside the stream, and which and the processing happens continuously as based on the processing time. Similar thing happens for batch. Uh, bounded and batch cases where we are not processing the streams, so there is no watermark which needs to be included. We already have all the data which we need in rest in the database or some place, some storage, and we can just take the data from those according to the windows that we are using and process those. So this strategy is generally used when we are trying to execute the same code for different types of input. One is batched input, another one is stream processing, which is for event-based stream processing or for processing time-based stream processing. Okay, so give me a second. So both out of bound and monotonic timestamp produces watermark relatively infrequently. So we provide a certain threshold after which it will produce the watermark. So it's not that frequently. And we provide the auto watermark interval, which is generally 20 milliseconds. By default, it is 20 milliseconds, so it will produce the watermark every 200 milliseconds. Not 20, sorry, 200 milliseconds. So raising this will increase the delay in the watermarks, which will increase the latency for each window to be processed, which will increase the state of each window to be maintained for longer period of time. So overall, the latency and storage will be retained for longer period of time if we increase this particular interval. An event is less if it is less than equals to common watermark. If you were to use a watermark strategy that produces watermarks at every conceivable opportunity, then every event without of order exceeding the specific bound would be treated as late. Obviously, if you are putting every watermark just after every event, um, then the latency will be high, but the late events will not be processed. But these built-in strategies only produce watermark. Okay, this means that some otherwise late events wouldn't be actually be considered late. So those are the events that we are talking about. That's why the this watermark strategy is used, right? Okay. So with these built-in strategies, lateness is not deterministic. Is non-deterministic. We can. Okay. So it's also right. So we have added this particular source, and in this source so there is this watermark strategy that we are creating out of bound watermark. The interval that we mentioned is 60 seconds, and you remember the two things. One thing is was the time stamp assigner, which assigns the event time. In this case, this we are taking the timestamp from the event, okay, not the stream record timestamp, yet considering the event time. And the window will be the strategy will use the 60-second late window. So the watermark will be produced when the event time is passed by 60 seconds. So for example, when the event time is 61 second, maximum event time is 61 second, it will produce a watermark for the one. And the time it will use will be from the event.timestamp, which is the timestamp assigner for each event in this particular strategy. And what we do here is we assign this particular strategy to this particular event, and which will produce this particular timestamped events So we are building this DAG internally, and we are processing. We are taking input stream and we're producing output stream. This is what the output stream will be: timestamped event after processing through this watermark and all, and this bounded litness. Okay. So applying the strategy after, so this is an example of applying the strategy after the source, after the Kafka event has been read by the data source of Flink, then this particular strategy works. But if you want to include the watermark at the source side of at the Kafka side, what it does is we provide the Kafka source, um, and we create a stream R out of this Kafka source, and we mention the watermark strategy. So whenever so this particular strategy is actually propagated to the Kafka, and Kafka actually inserts those watermarks in each partition uh, in a particular topic called Kafka, I guess, and produce those for each partition, and those partitions watermark events are passed to the source. Source takes the minimum of those and pass it to the further nodes. The similar thing we saw when we were trying to calculate the watermark for parallel streams in another example. So if you look at this Kafka, so for example, we went per partition watermarking. So watermarking is created for each partition. We generate each partition, combines them by taking the minimum add on the source data source of Flink, and then pass to the rest of the operators. Okay. Uh, Give me a second. Okay, now let's look at it. I've get caught up with my messages. Okay, so let's look at how it is done when we are doing uh, the watermarking after the source. So both of these partitions send the messages to source. Source sent to this watermark generator, which is a separate operator. It puts the watermark there and maintains overall watermarks for this particular node. Right. So when it has seen 77 as the maximum timestamp till now, right? So what it will do is it will mark its current watermark timestamp as 77 minus out of orderness minus 1. That's what the watermark this particular node will have. And similarly for this, it has seen 94, so the watermark it will have is 94 minus out of orderness minus 1. So both of these nodes will have watermark, and whenever the watermark changes, it will insert those watermark and pass those along the streams. That's one way of doing it. We are inserting the watermark. We have this intermediate operator, which is inserting the watermarks um, in between the stream. Uh, yeah. Okay, and passed down to the passed including into the stream and passed on to the next operator. Let's see what happens when we are doing it at the source. So in this Kafka partition, we have this watermark, which is according to the events that it is seeing in this. Each partition has a watermark assigned to it, and when that watermark event happens, it passes a watermark to this source, which is the Kafka Flink data source. It maintains a watermark which is the minimum of this. So in this case, watermark minimum of these two is 33 minus out of orderness minus 1. The same thing happens here. 18 minus out minimum of these two is this. The reason this one is recommended to be used is if we are including the timestamp in the Kafka partition. So whenever you are inserting the events in the Kafka partition, if you are using a configuration in Kafka which includes a timestamp in those events in the partition in each partition um, will be sorted, right? Because it's in a particular queue, so each timestamp will be in order, each events will be in order, and it's easier to maintain the watermark for those because the events are in monotonous order of the timestamp. So um, we don't have to actually maintain a maximum timestamp that we have seen till now to create a watermark out of it. We can just maintain the timestamp, maintain the watermark based on each event that we are seeing, and whenever the watermark changes, we include that watermark into the stream, and source automatically takes care of changing its watermark depending on the watermark uh, it has seen from both of these partitions. So it's easier to do. Uh, it's more optimized to do this way, and on the source side as compared to doing it on the uh, after the source. In this, we have to kind of maintain the maximum and for each stream which will come out of order because we are consuming from both of these partition, and when the event actually merge in the source they might become out of order, right? So it needs to maintain a maximum of it and needs to be passed through this intermediate node. So if you look at, there is an intermediate node and there is a maximum which is maintained as a state, right? For each key or for each node, right? There is a maximum state which is maintained, and and there is node which is used as intermediate state for each event. But in this case, we are not storing, we don't have that particular intermediate node, and we are not storing anything maximum. We are just keeping as the events are ordered in each partition. We don't have to do that. We are kind of using the propagation of watermark from each of these two partitions, and we are just maintaining a state of minimum of those watermark that we are seeing. And whenever this watermark changes, we include those into the stream. So this source is taking a decision. Each node takes a decision. There is no intermediate. So this is faster. I think this is more optimized. I haven't used it, so seems like it's more optimized. There is no intermediate state we need to maintain, but it's not always possible to include this into the source because Kafka has it, but sometimes we are not allowed to include that state, this watermark state here on the Kafka side. So it's not always possible. Or let's say there is another source which doesn't have this particular notion of watermark, then we cannot maintain. So in those cases, we have to do it after the source. But if it is possible, do it at in the source, I would say. So this is what it is saying. For mono, only requires the timestamp to be ordered within each partition. That's what I mentioned in the last slide. With Kafka, a timestamp assigner may not may not be necessary. The Kafka source will use a timestamp in the header. Okay, so with Kafka, a timestamp assigner may not be necessary. The Kafka source uses timestamp in the header of the Kafka source needed. You can override this simply using your timestamp assigner. So in your strategy, what you can, sorry, so with Kafka as a source, what you can do is you can, if you are using the timestamp from the Kafka source partitions, we can, so in the strategy that you are going to use, you can provide the timestamp assigner which actually extract the timestamp of that event which was assigned by Kafka partition, Kafka source, and use that as an event time. And as the Kafka source, as the strategy is assigned to each partition, those events which are occurring are sorted, right? Which are already in monotonous way. So this needs to be done to be used for it uh, for in-source implementation of Watermark. For in-source implementation of Watermark, we need to create Watermark on the source side, on the Kafka side, and we need another assumption that the events are occurring in order. And for that, we need to get the time of those events, and that time is assigned by Kafka. So we need a timestamp assigner which is extracting that time which was put into the event by the Kafka. So that's what it's going to do. So it has this Kafka source. It assigned this particular strategy that we talked about, and it mentioned it's doing it's sent this particular strategy to each partition of the Kafka topic and created the stream out of it. So if you look at this 33 minus 1, 30, each of the partition is maintaining its watermark. When it reaches a source, it maintains its minimum here, and each of these operators do the same. It maintains the minimum. Whatever watermark they are seeing from each of the source. For example, for this case, it's coming from this, it's coming from there. It will wait for, it will take the minimum of both watermark is seen from this and this, and maintain it in the locals to it. The same scenario we saw earlier, except that now formatting watermark strategy being applied by the customer. If you take a random understanding timestamp as an example, you should this will produce accurate watermark without imposing any unnecessary delay in row. Yeah, so another thing that we have when we are using this particular strategy of doing it in source is we don't have to wait for um, watermarks to be created because every event is in order, right? We don't have to wait for certain timestamp, certain delayed timestamp to come to produce a timestamp, to produce a watermark, sorry. So, so this will produce this the latency of the watermarks, which will be produced, will not latency, the frequency of the watermark produced will be more much better when we are doing when we know that the events are already sorted on the partitions, and this that will actually that will actually reduce the latency of processing the event for each time window. That will also reduce the time that each state is maintained for each operator. So overall, it will optimize the processing of the event and reduce the latency. Okay, so we'll talk about the idleness. Give me a second. Okay, so let's look at the idle sources. Okay, so it might happen, right? So let's, for example, we have this operator which has received 17 from this particular source, right? But for a long time, it has not received any watermark event from source 1. So the minimum that it will maintain will not be incrementing unless this particular input is sent from this particular source. So the watermarking will not go ahead. In that case, this the watermarking from this operator will not be generated. So there are so this is called an idle source scenario, right? So there are certain things we can do to handle this particular type of situation. Okay, and we can create custom, we can create our own watermark strategy and maintain idle time. It's one of the strategies that we can do, right? So there are different ways to handle it, but one of the things that we can do is we can have a state of when was the last time or when was the last time this particular node sent an event. And if the last time is greater than this particular threshold, then what we can do is we can take the minimum of the rest of the watermark that we have got, which is 17, and then we can just go ahead and watermark that, assuming that this is an idle node now and will not receive any events from this, and we don't want to stop the watermark. Okay, so with no events arriving, the order is no basis for advancing the curve, and also can cause the entire pipeline to stall, applying what we have learned about how what has been handled by two input stream, or it idle source could completely block the pipeline. Obviously, it will block the pipeline, right? If you are not providing watermark, it will those state that we are maintaining for each window will not ever be deleted. So we need to make sure that those states are deleted to maintain a healthy cluster. So one thing we can do is we can actually um, rebalance the idle stream with non-idle stream, but that's going to be an expensive operation. So what it happens is, so there is certain events which are handled currently by this, and certain events currently handled by this. So what we can do is we can divide the events among these two sources, reshuffle the events, then this source and both this source will have events to be sent to its next node. But this operation is expensive as we are shuffling the events across different nodes. We need to use network to send those events to different nodes and reshuffle across the cluster. So this takes time. This is more expensive operation. Or another thing that we can do is we can set the watermark for the node which is idle to maximum watermark. So what happens is, if let's say if this node is marked as maximum watermark, it will send that particular watermark here, and it will look at the minimum of maximum and 17. It will continue to send the events, continue to send the watermark as 70 to the as an output. So in the stream. We can do that. What we can do is after certain duration, we will just take the minimum of whatever watermarks we have from different input sources, and we'll just create the new watermark and send it as an output. We'll not wait for the idle node to send us a watermark in that case, and this is done via this. We are setting the idleness that we will wait for from each nodes that it is consuming the input from. So it could be a case where it is not even worth doing something out because the idleness is temporary, or if it is not temporary, then we can create a custom strategy which is done here, or we can provide the idleness time just like here. So a different way to handle it. This is more of a standard way. If you want something custom, you can implement something like this. Say it uses idle time, and it updates. It provides a watermark if the idle time is more than if we haven't got any watermark from certain idle nodes after a certain threshold. So let's see how long it is. Summary we have looked at from this one. It's already there. So trade-off between completeness and latency, we already talked about it. Different application, different needs. Latency sensitive application may need watermark to be produced more frequently, so we will have to compromise on the completeness of the output, or certain application needs more of completeness, and we'll have more latency in the output generation to accommodate for the late events. Does event time processing guarantees remain only if you never have late events? Because if you have late events, then it's not deterministic. Any event can come late into the stream and cause the output to be inconsistent across various runs. So it depends. The skew between the system and system clock and the latest time is event time lag. Okay, that's fine. The delay is necessary because we must wait. We like to reduce the lag as much as possible. There are trade-offs. You can understand that, right? That's what. I, so okay, so this is 35 pages. We are already streaming for 1 hour 51 minutes. So I'll just stop here, or I can go ahead. Let's see what we can do, right? Okay, so we'll go over it very quickly. Um, we've already seen that these are rich functions which can be keyed or non-keyed functions. Uh, I think we should do it later only because it's let's do it right now. Okay, so these rich functions have different timers. One is event timer, the other one is processing time timer. There is a state which is maintained. It could be keyed state or non-keyed state. Non-keyed doesn't have state, and non-keyed doesn't have timers also. So keyed state have timers as well as state, and non-key doesn't have any state or doesn't have any timer. Um, so there are side output we can generate when we are processing each event at the timer when we are processing each window. It could be any timer. It could be based on the processing time timer, or it could be based on the event time timer. For example, you are not able to produce or not pass something. You're not able to. Okay, so for example, you are not able to uh, handle a particular event, then you can produce errors in the separate side output. Uh, you can handle the late event and send the output to the side output that this particular event is late. We are just still providing the output in the um, side output if it required. So we have these two. Give me a second. Let me come back. Okay, so there are different process functions that are provided for in each which APIs. Um, so there is this process element which is called for each, which is called for each event processed by an operator, and there's this timer on timer function which is processed by which is processed when a certain timer is triggered, either an event timer or a processing time timer. And there's this output you can create out of processing each event. This is a side output, I assume. Okay. Of course, the timers only exist for keyed state, so it will have state, and this context is also there, which has a timer and other details in them. So we look at that next. So this is what the context contains. It contains the timestamp, time service, time domain, output, and current key. But this particular time service is actually used to set the timers, processing time timers and event time timers. Um, and this time service is register processing time timers, event time timers, get the current processing time, get the current watermarks. All of these functions are used inside those rich functions on timer function or process element functions. So one of the scenarios, one of the example that we are going to look at is a fleet of IoT devices each sending an event at least every 100 millisecond, requirement maintain an event counter for each incoming device ID. Emit an alert in the form of where if no event came for that device in the last 100 milliseconds. So let's think about it, right? How do we implement this one? So we implement this by maintaining a state for each device ID, which contains whether we have seen when was the last time we have seen the event in that for that particular device ID. So whenever each time we are producing event, we are each time when we are processing event in process event function, we are going to set a timer of 100 millisecond, which is going to be event time timer. And when so each time we are setting that, we are going to we are each time we are setting a certain timer, okay, and deleting the old timer, okay. Uh, when we are so okay, so let me clear that up. So whenever we are processing each element in process element function, process event function, whatever name that is, each time what we are going to do is we are going to delete the old timer that we created the last time an event was processed for this particular device, and we are going to create, if it was created, and we are going to add a new timer which is 100 millisecond after our current event time. And let's say we haven't got let's say the watermark timestamp increases by 100 millisecond and we didn't get any event for that particular device, then the on timer function will be called, and in that on timer function what we can do is uh, we can output the device ID, the device ID which is going to be the key, and we can output the count that we maintained when we are processing those element. So, so we have this state that we are maintaining, and this is the function. This is okay. So first we need to convert this stream into key stream, partition by key, and then we provide the process function. This is the process class that we have, and this process class has this process element and on timer function. And so we first of all create the configuration open function, which will be called when this this process this open function will be called when we first create uh, this process function for each operator. Whenever we start an operator, right, operator in a node, we call this open function to get the state, this particular state, keyed by the keys that we created here, right? Anyways, so we get the state here, and what we do in process element is we get the state, we check if we have ever seen any event for this particular device. If we have, we set the current to new state, we create a new state, or otherwise what we do is we delete the old timer that we set, increase the count for this particular device ID, and set the last processing time, update the timer here. So we deleted the timer, old timer, and we created the new timer to make sure that we don't trigger we don't we the reason for deleting the all processing time is that because it's not valid anymore. We've already got event which was before the 100 millisecond 100 millisecond threshold. We need to delete the old one, we need to create the old one, and we need to store this particular time in the last modifier, because the next time this event occurs we need to use that to delete the old timer. So that's why we need this last modifier, and this is needed to maintain the counter for each devices, because we need to output that in the timer when the timer is triggered. So this is a timer. Okay, give me a second. So another thing you need to notice is that it's using processing time timer, not the event time timer. And in this case, what we'll do is we have seen that whenever the on timer function is called, we know that we haven't seen event for this particular device ID for last 100 millisecond, and what we can do is we can get the state for this and produce the output in the out. Another example. Give me a second, I need to search something. Okay. Okay, so we are looking at another example where we are sorting the event stream. So the way we do it is um, so out of order stream to is sorted. So this is a stream that we have, and we need to sort this stream, I guess. So we have this buffer that we created, which is the state that we are creating. We are putting all the elements into this state, which is inserting in a sorted way. Okay, so this is a priority queue which we are maintaining as a state, and we are inserting each element into this priority queue. And whenever we see a watermark event, so whenever we see a watermark event, give me a second. So whenever we see a watermark timer, okay, so what we will do here is for each event we are going to set a timer, okay, and those timer will only occur when the watermark has processed or is increased to that particular timer's time. So this watermark will only produce when we have already seen, according to our watermark strategy, of course. So when it's so 15, it's so that the maximum is 15, and our watermark strategy has a out of bound threshold of 5 seconds, so it will produce a watermark of 10. So whenever this watermark 10 happens, we can actually remove these sorted elements from the priority queue and produce those as an output, right? Yeah. So how do we know that this particular watermark is inserted? We know it when the sorry, whenever an event timer is triggered. And for that event timer to be triggered, we need to put the timer for each event. Okay. So this will be outputted. So what we did here is we have this input keyed by this. There is this process function, process element. So what does this process element does is it has this time service, and each time. Okay, so this thing is done to make sure that we don't handle the late event. So if the watermark has already passed, then we will not then this will not go into this if condition and those events will be ignored. But if it is the current timestamp is greater than what current watermark, then what it will do is it will put this into the queue and add a timer, event timer for that particular timestamp. Okay, and what the next thing we are going to do is, and this on timer function will be called when a certain watermark is triggered, and when that watermark is triggered, we can output all the elements from the queue which are less than equals to that watermark. Okay, which we can output that we can extract those events from the queue and put it into the output. And yeah, okay, but this will of course perform badly because priority queue implementation is and removing the elements from priority queue is a little bit more expensive, so state needs to be Deceleration, serialization, I think is expensive for this. Yeah. Doing some state backing needs to reserialize every access and acceleration with something like priority is can be okay. Yeah, so priority key is not generally recommended, I guess. Do not use this as a reference solution for sorting, of course. Not. Something about timers. So what happens with this event, which is occurring as late event, right? So this will be ignored straight away because we have already put those if conditions there in the process element function. So some facts about timer are guaranteed on timer and process element are guaranteed not to be called concurrently. So processing the timer fires when the clock time of the machine reaches the timestamp. Okay, even timer fire. Okay, this is we already know, right? Generally okay to use a lot of timer. Timers are relatively inexpensive. You can afford to have lots of them. Have a timer per key with millions of keys, totally normal, but avoid having millions of them fire all at once because it needs to delete those times. Delete your timer, and if it is using hash internally, the bucket size will be huge, so it will not be open. So it will take more time to delete those. So that's why we should not have timer which have similar times, a lot of them. So for any given key and timestamp, there can only be one timer. Good. This is often convenient. It means you can safely create a timer without worrying about whether an identity already exists. After recovery, every event timers will continue to wait for a triggering watermark. Will be continue to wait for triggering watermark. Okay, so after, okay, so I think this is right. Okay, so each timer is actually stored in the state as well. And when let's say crash happens, or let's say we do checkpoint, those timers are also stored in the main storage. And when the recovery happens, those timers are actually loaded back, recovered back, and loaded into the memory and triggered based on whether it's an event timer or it's a processing timer. If it is an event timer, it will not be triggered. It will wait for the watermark to come. If it is a processing time timer, it will all the timers which were supposed to trigger during the recovery period, all of those timers will trigger one by one immediately after the recovery. But you can always key and otherwise in key stream. But timers are only present for keyed stream, right? So how do we make, what you can do is like you can create random keys for each events, right? But it should be deterministic. It cannot be random string. So it has to be deterministic. It needs to be derived from the message. It needs to be one-to-one mapping as well from message to the key, as we mentioned earlier. Um, or we can just do like create a random key for each, create just one key for each of the element and just process them. Um, yeah, we can always create a key, but it needs to be deterministic for each message. So there needs to be one-to-one mapping between the message and the key that we are creating. The processing function is a basic building block for event-driven application with Flink. Combining event processing state, time, timers are an important and flexible building blocks for analytical and event-driven pipeline, of course. It's optimal and less resource consuming. Of course, event-driven applications works like that. They need to scale for huge amount. So processing provides access to side outputs also. As I mentioned about error output, anything you can put in the put into the side output when you're processing each elements. Um, so there is a document for the mention timers. Okay, I think we have done this module. I will actually go ahead and to stop this stream. A little bit tired, so I'll do the next module later for this SQL, which is also interesting because the still now we were looking at an abstraction layer where we were processing the streams, right? So there is another layer which is put on the top of that streaming layer, which deals with SQL. You don't have to go and use these function. You can just directly use an abstraction or which abstraction which is communicated via SQL queries, and you can use that SQL query to actually manipulate or analyze the stream that I think we do that something similar in Kafka as well. So, but we do that also in Flink. We have that interface in Flink as well. So we look at those and we'll not go into details of each SQL query because there are a lot of combination which is possible. What we'll do is we'll quickly go over the SQL queries and see if anything substantial can be pointed out at that point of time. Otherwise, we'll go through it very fast. And we'll try to do both of these 4 and 5 module next time at a time. So yeah, okay. Good luck.